All right, let's dive right into this explainer and demystify the absolute marvel of physics happening inside your transmission every single time you change gears. Every time you pull that gear lever, you're actually triggering a small but extraordinarily precise mechanical event. It's this incredible sequence that literally converts the physical press of your hand into a highly calculated act of mechanical physics.
And think about this time frame for a second. We're talking 150 to 400 milliseconds. We have this tiny, tiny fraction of a second to perfectly match engine and transmission speeds without causing a catastrophic gear clash. In basically the blink of an eye, your gearbox has to accelerate or decelerate a target gear until both sides of the engagement point are spinning at exactly the same speed, because only then can the shift actually complete.
So how do we actually pull this off without double clutching like it's the 1950s? Well, we first have to introduce the real star of the show, the synchronizer cone. It operates on a deceptively simple principle of controlled friction. You've got two cone-shaped surfaces pressed together, and the resulting friction torque acts as a brilliant energy management system. It's just converting that relative kinetic energy straight into heat.
Here is our roadmap for this explainer. We'll be hitting the physics of shifting, the mathematics of cone geometry, materials science and thermal limits, diagnosing wear and fluid failure, engineering and manufacturing trade-offs, and finally, real-world impact and summary. Let's get right into it.
Section 1. The physics of shifting, focusing on energy and momentum.
For all the engineers tuning in, these 5 core equations dictate absolutely everything about the shift. They prove that a manual transmission is ultimately a masterclass in controlled energy dissipation. The job of the synchronizer is fundamentally an angular momentum problem. The friction torque generated at the cone surface has to overcome the speed difference, the delta omega, between the gear and the shaft. And here's the kicker. Because this energy dissipation is a squared relationship, if you double your speed differential, you literally quadruple the heat generated during the shift.
Moving on to Section 2, the mathematics of cone geometry, looking specifically at angles and wedges.
8.2 times. That is the magic number for wedge amplification. A standard 7-degree cone angle geometrically multiplies the physical force the driver applies by over 8 times. Because of the math behind the cone's half angle, which is 1 divided by the sine of that angle, the effective normal force pressing those cone surfaces together just becomes massive. This clever amplification is the whole reason a human hand applying a totally modest force to a gear shift can synchronize spinning heavy metal gears almost instantly.
But, it's never quite that simple. Engineers must carefully balance that cone angle, which is typically set between 6 and 8 degrees. If you make the angle too steep, it shifts incredibly fast, but you risk what's called a self-locking condition. That's mathematically defined as when the friction coefficient is greater than the tangent of the cone half angle. In plain English, the cone mechanically jams and refuses to release. On the flip side, if the angle is too shallow, you prevent jamming, but it takes significantly more effort from the driver just to generate the needed friction.
All right, let's turn up the heat. Section 3. Material science and thermal limits.
Take a look at this comparison of our 3 main friction materials. It perfectly showcases how engineers trade manufacturing costs for high durability and consistent friction. Solid brass or bronze alloys have been the industry standard for decades, right? They offer good friction but moderate wear. Then you step up to molybdenum-coated steel, which brings a huge improvement in durability, outlasting brass by 2 to 3 times. And finally, the heavy hitter, carbon composites. These give you the absolute highest friction coefficient and incredible wear resistance, but obviously at a much higher manufacturing cost.
And here is exactly why carbon composites are heavily preferred for racing. At 180 degrees Celsius, a traditional brass synchronizer actually begins to smear and glaze over, causing a sudden, massive drop in friction. Molybdenum buys you a bit of headroom up to 220 degrees, but carbon composite materials, they maintain stable friction characteristics all the way up to 280 degrees Celsius. In high-performance track environments, passive oil dissipation just isn't enough at these temperatures. You require advanced active thermal management, which makes carbon an absolute necessity to deal with those really aggressive high-energy shifts.
Okay, let's take this out of the lab and into the shop. Section 4. Diagnosing wear and fluid failure. If you want to diagnose a bad shift, you need a crucial checklist that distinguishes between general low oil quality, which ruins boundary lubrication across the board, and targeted mechanical wear on a specific gear's synchronizer. Transmission fluid plays a massive role here. It has to evacuate quickly off the cone to allow for friction while simultaneously carrying heat away. If you use oil that's too thick, it delays that evacuation and slows the shift. So if a vehicle has an erratic shift feel across multiple gears simultaneously, that is almost always a fluid breakdown issue. But if you're getting consistent grinding on one specific gear ratio, like second gear for instance, that points straight to localized mechanical synchronizer wear.
So, how do you know for sure the synchronizer is totally fried? Measuring the axial clearance, or ring gap, is the definitive physical indicator to diagnose stage-specific wear. As the friction material wears down over hundreds of thousands of shifts, the synchronizer ring literally sinks deeper into the cone. A brand new gap is typically 1.0 to 1.5 millimeters, but once it drops down to roughly 0.4 millimeters, the friction material is practically gone. At that point, the ring just cannot generate adequate friction torque, and replacement is absolutely required.
Let's zoom out to the boardroom now. Section 5, Engineering and Manufacturing Trade-offs.
To handle high inertia gears like first and second, engineers utilize multi-cone systems. This brilliantly multiplies the surface area to manage high torque thermal stress, all without making the driver push the lever harder. Because the speed differentials are highest in those lower gears, engineers will throw in double or even triple cone synchronizers. By adding inner cones, they mathematically multiply the total synchronization torque capacity. It solves the physics problem perfectly, though, as you can guess, it definitely increases the manufacturing complexity.
So the crucial takeaway for transmission design is this constant engineering tug-of-war. You're balancing component size, premium material cost, and flawless shifting performance. Executives and engineers have to navigate this really complex, multi-dimensional optimization problem. Want faster shifts? Okay, you need smaller cone angles or larger radii, but that increases your jamming risk and overall transmission size. Want maximum durability? You'll need carbon linings and multi-cone setups, which totally spikes your manufacturing cost. Literally everything is a carefully simulated compromise.
Finally, let's wrap this up with Section 6, Real-World Impact and Summary. Let's see how the driver actually impacts all of this.
Look at this massive difference right here. By utilizing rev matching to equalize speeds before downshifting, a driver can drop the thermal energy load on a synchronizer from over 1,500 joules down to just 15. When you blip the throttle to max the engine speed to the gearbox, that speed differential, the delta omega, approaches zero. And remember our equation? Because energy dissipation is tied to the square of that speed difference, dropping it to near zero means the synchronizer does almost zero work. That is a reduction in wear energy of over 100 times for a single shift.
This proves beyond a shadow of a doubt that synchronizer engineering is absolutely essential for vehicle performance, longevity, and ultimate driver satisfaction. A healthy synchronizer is designed to be a completely silent, invisible guardian of your gearbox. It acts as a blocking mechanism, physically preventing the gear from engaging until synchronization is 100% complete. When you force a shift and hear a grind, that isn't just a bad noise. That is the literal sound of friction physics failing to cope with kinetic energy.
It really leaves you wondering about the sheer genius hiding inside your gearbox, doesn't it? If a single machined cone weighing just a few grams can handle hundreds of watts of power in milliseconds, what other hidden physical marvels are operating silently in your vehicle? The next time you effortlessly slide a manual transmission into gear, just remember, you are initiating a masterclass in thermal limits, geometric wedge amplification, and angular momentum, all happening flawlessly in the blink of an eye.